So, while we wait a couple of more minutes, how have you been doing? Are you tired by now of Python after 7 weeks of it? Well, it would seem that way. Anyways. Oh, okay. So I don't know if I'm able to change this, but Philip, today's TA, is on the attendee side, while he should be on the panelist side in order to fulfill his role, I guess. Can someone do something about it?
It should be fixed.
Okay, great. Thank you very much. Hi, Philip. Thanks for being TA today.
No problem.
Okay. Hmm. So we don't have much interaction for now, I guess. Some fatigue must have settled in by now. It's understandable. I'll try to make it as fun as humanly possible. But, you shouldn't take my word for it. You should give me some feedback. So if there's something that can be done about it. I see more people pouring in. Hello, everybody. Hello, everyone. Thanks for joining. So new people, how are you doing? Hello. Finally, a brave soul that answered. Hello to you as well. All right, let me check the time. So I'll repeat the question since now we have doubled number of attendees. Has anyone here already been present to the previous lecture, the Tuesday lecture? If so, do you have any question about what we saw in last lecture? Any feedback about the way I gave this presentation? Anything at all? If so, please type in the Q&A section. All right. Thank you very much. I appreciate it. So if there is anything about the exercises on fitting that you would like to review at the beginning of this lecture, please do write it in a Q&A. So before moving on with the next topics, I will have a short review of whatever you want to see again. Otherwise, in a couple of minutes, I will just begin without further ado in the following topics, okay? All right. It seems that somebody has had some problem with the plot. All right. Could you tell me what happened? Like the command went through, but no plot appeared. What happened when you run the code? Hmm. Okay, that is unexpected. So let me just run a moment the notebook from last time, like this one. So let me just go very quick. Just up to the first plot. All right, this is like the first plot. So if you run these first 3 cells, you do not get this plot here, for example. Is that what happens? Okay, I'm really not sure about what is going on. It might have to do with your own notebook or with the packages you have installed, but since running the same code on my end produces these results, I'm afraid that I don't know what's your specific issue. I don't know. This code, Python specifically, is made for being portable. It means that usually if I run it on my machine and you run it on your machine, it does the same. But, nothing's perfect. So this kind of things might happen. So if you want to solve it, you can look into it and you can Google it. That's what I would do. So you can try to see what happens in that case. I'm sorry for that, by the way. These kind of things should not happen. No problem at all. That's what I'm here for. Okay, it's now 12:06. So without further ado, let me begin today's lecture. Hello again, everyone. Hello also to the YouTube stream audience, if there is any. My name is Roberto Bruschini, and I will be giving today's lecture on magnets and symmetries, which should be the last lecture in the series of Python for STEM. I hope you enjoyed this course very much. I am glad that I got to do this concluding session. And since we have already covered the previous part, let's dive in today's lecture. I will just review briefly the magnet, spin, and interaction section that I introduced last time. I will correct a mistake I did in presenting. I said something incorrect last time. So whatever I'm going to say today supersedes whatever I told you last time. And after a quick review, I'll move on to these more abstract, but yet beautiful and useful concepts of symmetries and degeneracies. And after a whole lot of theory, when you're fast asleep on your chairs, only then I will put you up with some code and show you how to actually explore these concepts using Python. Now, magnets. All right. So I already shown you this picture of what happens when you put a magnet in contact with iron filings, spread it over a piece of paper. And you see this beautiful pattern here of these lines going from one end of the magnet to the other. And this pattern arises because the magnet generates a magnetic force. And this force works in such a way that opposite poles of magnets attract each other and like poles repel each other. And this makes so that you can distinguish the poles of a magnet because they're different from each other. So you have a north pole and a south pole, and these guys interact in such a way as shown here. The Earth itself, as a matter of fact, works as a gigantic magnet with a very weak magnetic field, and it is this magnetic field that makes so that a compass always points to the north. So since I just told you that unlike poles attract each other, this tells us that the north magnetic pole is actually the north geographic pole is actually a south magnetic pole and vice versa. And using this metaphor of the compass, we can interpret these lines that appear when you put the magnet on the magnetic filings and the iron filings as each of these tiny iron needles being a compass that orients itself along the lines of this magnetic field generated by this magnet here. So where the magnetic field is very intense, all the findings are aligned with each other, and they form these lines here that kind of allow us to visualize where the force flows, how it goes. Whereas far away from the magnet, the field is very weak and the iron filings are hardly aligned at all. This allows us to explore visually the relation between magnetism and electricity. In fact, we can do the same game of putting iron filings, but instead of a magnet, we put there something like an iron ring. If there is no current flowing in this ring, nothing happens. But in the moment we turn on the light and current starts flowing in this ring here, then the iron filings make this pattern here, which is exactly the same as those from a magnet. So what we understand from this is that if you have an electric current flowing in a loop, this behaves like a magnet. Last time I told you something incorrect, that is that the current must vary in order to create the magnetic field, but that is not correct. I was confused because the contrary is true. This is, if I have an external magnetic field and that magnetic field varies with time, then this can induce an electric current. This is another aspect of this electromagnetic interaction that is not interesting for now, but I wanted just to explain what got me confused last time. So, an electric current flowing in a loop creates a magnetic field like that of a magnet, and depending on the geometry of the conductor where this current flows, you have different lines of this magnetic field. You see, if your conductor is just a straight line, then the magnetic field behaves like circles around this line here. If you have a ring, it behaves in this way, where the magnetic field is strongest at the center of the ring, and then it does this pattern away from it. And if we stack many rings in what is called a solenoid, we get this magnetic field, which is extremely strong inside here, and it's much, much weaker outside from this cylinder. So, do you have any question? No? So let me go on with the last part of the review. So what happens is that not only the currents inside a loop generate a magnetic field, but in the moment this happens, the loop itself behaves like a magnet. So if we take a ring, we make current flow through it, and then we put this ring with the current inside a magnetic field generated by, for instance, another magnet. What will happen is that if the magnetic field of this ring, which is described in physics via a quantity that it's called the magnetic moment. So if this magnetic moment is anti-aligned with field, then there will be a force that pulls it through where there is a lower density. So anti-aligned, yes. All right. So it pushes it away. Whereas the contrary is true, that if the magnetic moment is aligned, then it will feel a force that pulls it where the magnetic field from the other magnet is strongest. So this is to say that these currents inside the loop behave just like a magnet in the way that unlike poles attract and like poles repel. Therefore, if we want to understand where the magnetism inside the material comes from, we can use this as an analogy. What if inside some magnet, like this one in the bottom right here, is magnetic because inside it we have many currents circulating in microscopic loops? This is more rigorously defined in physics by thinking that this material is made of, atoms, and atoms are made of nuclei and electrons. And these electrons might be imagined as a very, very tiny ball charged with electricity that spins on its axis. And this spinning ball of electricity generates a magnetic field in exactly the same way as a current circulating in a loop does. So with this analogy, we might imagine that some material that is not magnetized is made of many magnetic moments associated to electrons or to atoms or to more complicated stuff, but magnetic moments that are not aligned. They are randomly distributed along any direction. So if you sum the magnetic field of all of them, you get 0. On the other hand, a magnetized material can be interpreted as some material in which all these tiny magnetic moments happen to be mostly aligned on some axis, so that the resultant of this magnetic moment is some big magnetic field that exits this material here and generates those magnetic field lines that we see with the iron filings. Is this clear to you up to now? Is there any question about this? If not, then I'll assume that I'm doing a good job, and let us move forward. So one of the first mathematical models to describe the kind of physics I just told you about is due to Ernst Ising, who made the so-called Ising model that you can find also in this Wikipedia page. Ising, in his PhD thesis, solved the simplest version of this model where, all these magnetic moments live on some sort of one-dimensional line, which is the simplest situation. In these Ising models, the spins are fixed. They can either point upwards, to which it is assigned a numerical value of +1, or they can point downwards, to which we assign mathematically the number -1. So what is described in this model is that these spins inside the material can either align or anti-align, which means they can either be both +1 or +1 and -1, and so on. What this model aims to describe is that depending on the specific material we're talking about, it might so happen that alignment of these spins and therefore magnetization is favorable. Whereas for other materials, it is not so favorable, and the spins are, let's say, less keen to align to each other. And the way Ising wanted to describe this is to take these spins, make them live on a one-dimensional curve, like in this case, we make them live in a ring. So each of this spin is represented by this ball with the arrow pointing in one direction or the other. We assign to spins pointing upwards the value of +1, and to spins pointing downwards the value of -1. I see we have a couple of questions in the Q&A. Doesn't the Pauli exclusion principle say that electrons have to have different spins? Okay, so to answer that, Pauli exclusion principle applies in the case that the two electrons you are talking about are indistinguishable by all means bar the spin. So Pauli exclusion principle says that two electrons cannot have identical states, where the state might include the spin, the velocity, and many, many, many other features. So if, like in the case of the material, you have many electrons that differ not only by the spin values, but by many other features like the atom they're bound to or other complicated physical features, then they can have the same spin. It's important that they live, let's say, in, for instance, slightly different locations, all right? So you can still, in a certain way, say that the Pauli exclusion principle works because you have more degrees of freedom by which you can make these electrons not in the identical state. Or do magnetic, so the follow-up question was that magnetic materials have to contain odd numbers of electrons, and I would not say that this is the case. It's more the fact that you have many ways of combining the spin of the electrons with their other degrees of freedom in such a way that you do not fall into Pauli's exclusion principle. No problem. Thanks for asking. So let's go back to our spins, 6 spins in a ring in this example here. To make something, quantitative out of this, we need to assign labels to them. So we call each spin with a number 1, 2, 3, 4, 5, 6. And so we assign an index in order to write more compact mathematical expression that just goes from 1 to 6. Sorry. And we will call the spin of each of these guys as S sub I, which means the spin in location number I. So we can translate this figure over here in 6 numbers. S1 is +1, the second one goes down, so S2 is -1, and so on and so forth. With these definitions, we can make a somewhat general model of the energy of those 6 spin in the ring. What Ising came up with is this sum of 3 terms in which you have some multiplications or some sum of the spin states, and you have 3 constants, A, B, and C. The idea is that we would like to be able to capture the difference between different materials, and so how much the spins are adapt to aligning or not. And we would like to encode this complicated information in 3 numbers, A, B, and C. That's pretty much captures the philosophy of physics. I mean, these magnets are extremely complicated. There are innumerable electrons and innumerable complexities. But in physics, we want to reduce all of that complexity down to a few numbers. So we want to, now understand what each of these 3 terms does. The first term here multiplies the value of a spin by the value of the spin next to it. And so this we will see in a short while. It has to do with the idea that these 2 spins interact with each other via their own magnetic fields. This second term here multiplies the first spin by the second next spin. And so it is a similar one to the first, but it has, let's say, a longer range. And then the third one just acts equally on all the spins. So let us understand this in concrete cases. Let's take, for instance, the first spin. For this one here, the first term is +1, and the second one is -1. So the first term is -1. The second term is also -1 because we have +1 times -1, so this is also -1. And the third term is just +1 because the spin goes upwards. In this table here, you can see all the different values and combinations so that if you want, you can check by hand what this energy looks like for each of the spins in this example. A small technical note somehow, in order to this sum here to make any sense mathematically, we need to imagine that the 6th spin is closest to the first spin, so that I +1, that would be 7 for 6, is actually 1. And this trick here is called periodic boundary conditions. And this is why it is useful to imagine this guy living in a ring. So it's pretty intuitive that the closest neighbor to 6 is 1. So I anticipated that each of these terms has its own physical intuition, and you might have started to realize that the first term is somehow resembles the idea that like poles attract, like poles repel. And as you see, this term makes so that you see that the energy of the spin changes depending on whether the spin next to it is aligned or anti-aligned to it. And the strength of this effect depends on the value of A. The bigger is this value, the more this interaction between so-called nearest neighbors is more intense. We have a similar effect for the second term, where we compare the spin of this guy with the second nearest neighbor. And this is called, unsurprisingly, next to nearest neighbor interaction. And in this case, it's regulated by this parameter B. And finally, the third term that acts equally on all the spins, it's very much like if we had an external magnetic field, like an outside magnet, whose effect tends to influence the spin states, because as I told you, the magnetic moment tends to be anti-aligned with the field. So in a moment, I will finally begin doing some Python numerical work and show you how one can calculate all of those stuff numerically. But in order for us to understand the results we're going to get, I need to introduce you first to some useful physical concepts. And this concept is that of symmetries and degeneracy. Before I move on, is there any questions about what we saw before about this energy here or the meaning of these terms? It's important that you have some intuition of what this means before I move on. So if you have any question, no matter how silly it might seem to you, or if I just have to repeat something, just type in the Q&A. See, we have one question, no questions. Nice. So if nobody else has questions, let's move on. Okay, so we will be calculating the energies in this Ising model for many scenarios. And we will see that some of them are the same for different spin states and some of them differ. And in order to interpret what is going on, we will be using the concept of symmetry. Symmetry, you might have a, intuitive knowledge of what symmetry is. Symmetry means, for instance, that we have a curve like that, and if you draw a line right in the middle, the two parts on the left and right of this line are just the mirror of each other. Whereas this curve here, if I do the same game, it's not symmetric because this line on the right is different from the mirror of this line on the left. Somewhat less intuitively, this idea of symmetry can be seen not as separating this curve in some parts, but rather as the idea of making some transformation on this curve and seeing if it remains the same or it changes. Namely, if you take a mirror and you point it at this shape over here, you will see that the reflection is exactly the same as the original image, which is to say that this thing here is symmetric under reflections. We can define some symmetries also for the spin states we're playing with, these spins pointing upwards and downwards inside a ring. So how many symmetries and which symmetries do we have in this Ising model? To begin with this, answering this question, we just turn off the magnetic field so that we throw away the last term and we're left with just the first two. So one might verify that if we have some spins in a ring, they have a certain energy. And if we rotate these spins, like in this case here, we rotate them counterclockwise by one space, you can see that you can calculate this and actually see that the energy is exactly the same. And this is the physical way of saying that these two are symmetric on the rotations. They have the same energy, and therefore this model here is symmetric on the rotations. There is a question here for you to answer, is that how many distinct rotations can we have? How many distinct rotations of this ring can I generate? How many of these figures can I make that are obtained from this by rotations and are different between each other? I have one here, I can make more. How many? This is an actual question, if you want to answer it. Okay, so we have a couple of answers. So the first answer is more an answer to the question of how many different spin states I can make. And the second answer as well, particularized to the number of slots we have. My question perhaps was not clearly explained. If I have already this spin state, and it's this one, and the only thing I can do is rotate it, then you can see that you can rotate it 6 times. After 6 rotations, I come back to the original configuration, and so that's not anymore a new rotation. Other than rotations, we have reflections. So we draw a line in here, and then we exchange left and right of this line. And these two guys as well have the same energy. So we can say that this model is also symmetric for reflections about any axis. And finally, we can also take each of this spin and invert it from +1 to -1, from -1 to +1, and vice versa. Now, another question for you. So you can trust me if I tell you that these two guys have the same energies in this case, where we have no external field. But based on the intuition we have tried to develop so far, would you expect these two guys here, left and right, to have the same energy if C is not 0? So if we have an external field, what would you expect? What is your guess? Yes or no? Do they have the same energy if C is not 0? All right, so we have 2 people who told that it will change, and this is true. In general, it would change. It really depends on how these guys are aligned or not. So it might so happen that they do have the same energy, but if there is an external field, they also might not have it. So the symmetry on the inversion of all the spins is not asymmetry if C is different from 0. Very well done. Now, let's go on with a warm-up question. If we have n spins in a ring, how many different spin states do we have? Actually, you can skip this question because you answered that earlier. You told me that we have 2 elevated to the n, where n is the number of spins, and that is correct. So if we have, for instance, three spins in a ring, then we have 8 distinct configurations. And each of these way of combining spins up and down in a ring is what I've been referring to all this time as a state. And here, since there are just 8 of them, we have put them explicitly. We have the one where all of them are up. We have the one where all of them are down. Then all the different possible combinations of 2 spin up and 1 down, and 2 spin down and 1 up. Now, you have almost all the instruments to finally dive then into the programming and understanding how this Ising model can help us develop an intuition of magnets. Is there any question about what we have been seeing in the last few slides? Because if not, we can move on to some actual solution of this model. I will assume that there is not, and don't worry to ask questions about stuff that I've covered before. As soon as I have time, I can come back to it. So let's go on. We have this, in general, we have this perception that things tend to go towards the minimum of their energy. This is, if the water flows downwards. If I hang a picture on a wall, the picture tends to go below the point we have hanged it, not above it. In general, things in nature tend to go in a way that the energy budget is minimum. So with the examples I was making before, if you think of a ball in the presence of gravity in a slope, this will always go downhill. Since what the energy would be at the minimum of the ball would be at the minimum of the energy if instead of being up here, it were here. So the ball will try to be the ball that is sitting here and will roll down and then come up and roll down again, endlessly trying to become the ball at the bottom here, which is called the ground state. So what we will be looking for, and it will be the most important feature of this Ising model, is the ground state, because what the ground state of the Ising model is will tell us what is the most favorable configuration that we will find for our magnet or our system of spins. So we will look at the ground state of this system of spins in a ring, and we will observe that some of them have some ground state that is not just one state. It's actually two states. We will see, for instance, that these two states of some model are degenerate. They are, for instance, both the ground state of your model, or in general, they have the same energy. So if I tell you that these two states have the same energies for all the possible values of the parameters A, B, and C, you can trust me that it is like this. But you could ask why? Why do these two guys have always the same energies? Do you have any idea on how these two spins, the ring on the left and the ring on the right, might be related to each other? Is there some, let's say, transformation that allows me to take this guy and make it the same as this guy on the left, or vice versa? Yes, very good. It is a rotation. You've earned the small nerdy face badge. That's the correct answer. These two states have the same energy because they're related to each other through a rotation. We have a second answer, which says that the charges are interchanged. And in this case, in this particular case, this is also an acceptable answer, but it's contingent on the fact that the sum of these spins are zero. If this was not like this, then one would have need to be more careful, but that's also a correct answer for this case. So another question again. Now, are these two states on the top here, the left one and the right one, always degenerate for all values of A, B, and C? What do you think? Are they always degenerate, or they are degenerate only for some peculiar values of one of these three parameters? All right. We get one answer. Maybe not all values. This is correct. Okay, so you correctly pointed out that it's not for all values, and I can give you more precise indication. These two guys are related by a symmetry, and the symmetry is the inversion of all the spins. You see, everything that goes up in here goes down in the rightmost part, and vice versa. And you may recall that this symmetry is not a symmetry of the Ising model in general, but it is if C is equal to 0. So these two are degenerate only if C is equal to 0. Now, second question. Are these two states always degenerate for all values of A, B, and C? Come on, you're doing good. Let's see if you get this one as well. We got 1 on the side of yes. Anybody has a different opinion? Okay. The correct answer is yes. And there are 2 different reasons for that. You can either see that these 2 guys are related by a rotation. Are they? No, they're not. I want to be sure about it before I say something incorrect again. They are not related by rotation. They are related by a reflection along this axis here, as you can see. And also, they are related by an inversion, which is usually not a good symmetry if C is different from 0. But in the particular case where the sum of this spin is 0, like in this case here, you can see that even if C is different from 0, now the sum is 0. So accidentally, this inversion symmetry is again a symmetry of this model, but not for all states, only if this sum is 0. We can finally, for everybody joy, we can finally do some Python programming. So we want to now define a Python function that takes the Ising model, it takes a spin state, and gives us back the energy. How do we do that? We are going to write a code that allows us to compute each of these 3 terms and then define a Python function. So let me go to the notebook, and here we are. Okay. You might remember from last time that, no spoilers again, that when I do these exercises, I also like to give you a couple of practical programming hints. So last time I tried to convince you that it's good manners in programming to put the imports at the beginning of your code. So here it is. We are going to be using matplotlib pyplot to plot stuff, and then we will be using numpy, which has very many useful functions for us to play with. So exercise 1 boils down to defining these 2 functions. These first functions take an array of values and rotate it to the left. Why would we be doing so? Because as you see previously here, you can imagine each of these spin states as an array of values +1, +1, +1, or -1, +1, +1. And if we want to compute these kind of interactions, then what we want to do is to compare different positions. And we can do so by rotating these vectors of spin. So this function here takes the spin state. Then it creates a temporary variable, which has the same length of this initial variable and is filled with zeros. Then it fills the temporary variable with the same values of the initial state, but with the position inside the list shifted to the left by 1 position, and then returns the state rotated by 1. And with this, useful function defined here, we can now easily define the energy of the Ising model. Let me take this and put it right next to the expression. So the energies of a spin state ST in the Ising model as a function of these parameters A, B, and C is going to be calculated from the spin state itself, the spin state rotated by 1 vector, and the spin state rotated by 2 positions. The first term here is going to be A, the first parameter, multiplied by this sum. This sum is the sum of the state itself multiplied by its version shifted by 1 position. So this is what the SI times SI plus 1 means. Similarly, the next to nearest neighbors is obtained by multiplying B by this sum, which is nothing but this sum of SI, SI plus 2 on the right. And finally, the background field it's just this term made by C multiplying the sum of the spins. We sum the three contributions together and we end up with the energy of the Ising model. Let's run this cell and go on. Now, the second exercise here is to write a code that lists all possible configurations for n spins. Now, we know that for n spins, we have 2 elevated to the nth power number of possible spin states. And if these states are a few, like 8, we can by hand figure out all of them. But if we have like 10 spins, then we have 1024 spin states, and good luck in filling all of them out by hand. So we want to automate that. So we can write a useful code. If I can get to open this guy, yes. And the code that lists all possible states of n spins is the subject of exercise number 2. So, as I said, if we have n possible spins, we have 2 elevated to the n possible states, and we want to put all of these states into lists, starting with a single spin that is up or down. So this is the very first thing we begin with, a state of a single spin being either up or down. Then we have a for loop for n from 1 to n minus 1, from 0 to n minus 1. And we want to remember how long is our list. And then for each value of this iteration, we make copies of this spin state, and then we add +1 to the first state, -1 to the second state. And in this way, we end up with the states of 2 spin. Rinse and repeat for how many times you want, and at the end of the day, you end up with the states of n spins. The details of this code should be quite understandable to you using the the tools you have developed in previous lectures. So I will just go on. But if you have any questions about this code, which you should be able to access on the Dropbox, just type in the Q&A at any moment. What I will ask you to focus now on is the fact that, you see, this function here has some lines that are either beginning with this hashtag over here, or they are enclosed between these quotation marks. As you see, Python knows that these lines mean something different than the rest of the code because you see they have a different color. So this portion of the code here, they are called comments. And these comments are completely ignored by the computer. It's just there for us. It's there for us to understand what the code does. As you see, just from having a look at these lines over here, you wouldn't know what this function does. So I put this in plain words, in plain text, inside the code. So when you go through the code yourself, you know what each of these functions does, and this will help you immensely in understanding the details of the code. This is not just something that I do because I'm teaching this class. This is something I always do when I program. Commenting your own code is very useful to anybody that is going to use your code. And there are very high chances that if you work in the STEM, somebody is going to use your code. So the second programming tip I'm giving you is to always comment your code. You don't need to write a whole documentation for it. Just put a line or two in the most important parts that explain to somebody else what your code is doing. Now, let's move on then. Another good practice is also not to wait until the very end result to check whether you have made mistakes in your code. It might be a good idea to take the functions we have defined, like Ising lists here, and test for some value of n if it works as intended. If, for instance, we found a mistake in this, we want to know this before making more and more code that relies on the function, because if we wait too much, it will be very difficult to spot the mistake in a very big chunk of code. So let's just test this function for 3 spins. So we expect 8 states, and guess what? We get 8 states, and they are exactly the same states of the slides I showed you before. These guys over here. You see? They're the same. 1, 1, 1 is the same as this guy. Minus 1, 1, 1 is the same as this guy, and so on and so forth. So this function does exactly what we expect it would do, and is a nice thing. And it's just a point of information. This procedure of taking your code, you run it, and you compare it against a result you already know how it should be, is sometimes called debugging. If the result of this code were different from the slides, then I would be 100% sure that there is a mistake in my code, and I would need to look for it. Then, on to more complicated exercises. Exercises 3 to 6 ask us to calculate the ground state energy and the degeneracy for the Ising model with many different values of the parameters. The degeneracy, recall, is the number of different ground states that have the same energy. So we will do it for these values here, then 3 times for these values that are all quite similar, and then for this last set of values. Let me go back to this. All these exercises from 3 to 7 are quite similar. So we can be smart about it, and instead of doing a lot of different portion of codes that repeat themselves, we can make just one function that calculates the ground states, and we can then apply this function to all these values and get the answer. This is a quite complicated function, so I will try to get into detail now. This function here takes as argument the number of spins, the 3 parameters, and returns the ground state energy and the spin states associated to these lowest energies that are the ground states. So first of all, we use the function that we defined before to create all the possible states of n spins. Then all this portion here, what it does is it finds the ground state it finds the ground state energy, and in doing so, it saves inside a list all the possible spin states that have that energy. So what this is doing exactly is that it begins with a guess of the ground state energy that I know for sure it is wrong. In fact, I put the quote-unquote ground state energy to plus infinity. So we know that this cannot be the ground state energy, and whatever the code finds later on will be better than this initial guess. And the ground states list is initially empty. Then the code goes into this for loop, and for every state inside the list of all the states, it calculates the energy. There are then 2 possibilities. Either this energy of this state is smaller than our guess for the initial state, or it is equal to the initial state. It cannot be bigger because the first one is infinity. So if it is smaller, which in the first case will always be, then the program knows that it needs to update its guess of the ground state energy to the energy of this state, and then it appends this state to the list. It creates a new list of ground states of which the sole member is the new state. Then we move on later on. Again, for the next state, you calculate the energy. Now there are 3 possibilities, but we are only interested in 2 of them. Either the energy of the new state is smaller than ground state, then we do what we did before again, because we need a better guess of the ground state energy, or the energy is the same as the previous energy. So what we do is just append the new state to the list of states with the same energies. So this can seem quite complicated, but the idea is that by the end of this loop, this guess here will be the actual ground state energy, and the list of states with the same energy will be the list of ground states. Again, let's see if it works. We just plug some values of the parameters that I don't care what are they precisely, and I calculate the effect of this function and print the results. let's see, it's taking some time because as you can imagine, there are many states, and there you have it. So it gives us a number for the ground state energy. It tells that the degeneracy is 2, and in fact, it gives us the 2 ground states. This is one, and this is the other. There are 2 of them, they are distinct, and therefore the degeneracy is 2. Then, thanks to this useful function, now we can do all the exercises from 3 to 7. We just need to change these parameters here and reevaluate. So let us begin. Exercise 3, n equal 3, a equal 5, b equal 1, and c equals 0.01. Let's run again. There you have it. There is a ground state energy, and it's 3-fold degenerate. Now let's try the exercises 4 to 6. In this case, we have n equal 10, a equal -5, b equal 1, and c that goes from 0 to 0.01 and -0.01. Let's begin with 0.01 since I already have it here. Okay, now we have just one ground state. What if c is 0? The energy is slightly higher and we have 2 degenerate ground states. And what if c is -0.01? And now again, we have only one state. Let me copy this cell a couple of times. And let me put all these results at the same time so we can compare to each other. 0 and this. 1, 2, 3. Okay. So the exercise in the slides asks us to make sense of these 3 results. What do you think about this? How does the ground states from these 3 results compare to each other? Any idea? Do you see any similarity between these and these 2 and these 2 and this one? Okay, someone says that it is the same. Well, more than saying that it is the same, we can find this one here and this one here both inside here. So the way we interpret this is that both these states here have the same energy if there is no external field, but in the moment we turn on the external field, one of these 2 will be more favorable from the point of view of energy. And it comes to no surprise that if the external field goes down, then the spins want to be anti-aligned with it. And so it's the states that goes up that is favored. And contrarily, if the external field goes down, then if the external field goes up, then our spins want to go down. So finally, we can go on to exercise 7. Glad that I explained that correctly. Now let's go to exercise 7. Let's remove these redundant cells and let's put 15, B 0.2, and C 0.02. Would you look at that? We have many degenerate states and some low energy. Very good. So we have 15 different states. Do you have an idea why are there 15? And I'm going to tell you, there couldn't be more. How do we know that? The answer is that these guys are all rotations of the same first guy. And since we have 15 spins, we can only have 15 different rotations. Let's go on. exercise 8. Now, we will have 10 spins, and so we will have an awful lot of distinct states, and we will fix A and B to some values. What we want to know with this exercise is how do the ground state or states, if more than one, change if C is equal to 0 versus minus infinity. So let us fix the parameters that are not going to change, N, A, and B, so that we don't have to worry about them anymore. Question number 1, what is the ground state when C equals 0? Question number 2, what is the ground state when C is equal to minus infinity? Well, these two questions are basically the same as exercises 3 to 7. Is that right? We just need to evaluate this function by changing C. So let us begin with C equals 0. All right, we have two states. All right, and they are just the rotation of one another, or the reflection, if you want, by inverting all the spins. And so this is the answer to question number 1. And if I go back to the slides, you can see that this is actually the same that we get. In fact, sorry for the mess. Okay. Let me put this side by side. And now you see that, recall that -1 means arrow pointing downwards and +1 means arrow pointing upwards. So you see that this state here that we get from our Python function is the same as the top row here. And this state here that we get from our Python code is the same as this state down here. Now, trust me that we will need this state later on in the following exercise, so I will just save this into a variable that I called ground state Q1. And, oh, I already spoiled this. I was planning to ask you why these two guys have always the same energy, but I already told you why. So let's move on. And let's do question number 2. So we cannot actually put an infinite value in this. You might know that computers are not very comfortable with infinities, but we can get more or less the same effect is if instead of C minus infinity, we put just a very big number. And then as you see, we do get the correct answer that the ground state is the one where all the spins are pointing upwards. And here in the slides, the physical intuition that, of course, the stronger the magnetic field, the more the spins want to align or anti-align to it. Again, we want now to save this ground state in a variable, and let's go on. Exercise 8 continues with now 2 follow-up questions. Instead of taking C equals 0 or infinity, we are asked to vary it continuously from 0 to -3. We know already that for C equals 0, these are the ground states. We saw that before. And we also saw already that for big and negative C, this is the ground state. The 2 questions are, at which value of C as we decrease it, these 2 are no longer the ground state. And the 4th question is, at which point while we decrease C, this will become the ground state. So answering these questions theoretically, might be somewhat difficult. Ask Ising, who created the model, but we can do something simple thanks to Python. If I can move this down, oh golly. Okay, there. All right, so another thing that computers don't like other than infinity is continuously. Nothing in a computer can be continuous. You know that a computer is made of bits, 0 or 1. There is no continuity. But we can emulate continuity by making an array of values from 0 to -3, and we divide them in a grid of points. So we make a list of 50 numbers ranging from 0 to -3. And this is the closest you can get to continuity with a computer, but it's good enough. Then we will want to, oh, this is a mistake. We want to initialize these 3 lists in which we will put, on the one hand, the ground state energy, and on the other hand, the energies of these guys. This is the ground state from Q1, and it goes in this list, and this is the ground state from Q2, and this goes in this list. So how do we do that in practice? We do a for loop, and for each value of C in this list of values from 0 to -3, we calculate the ground state energy, and we save that in its list. We calculate the energy of the ground state from Q1, and we put it in this list, and we calculate the ground state energy from the state from Q2, and we put that in this list. And from this, we would be now able to answer questions 3 and 4. These are not going to be the ground states anymore in the moment that EQ1 is bigger than EGS. And the answer to question 4 will be the moment in which EQ2 becomes equal to EGS. But instead of checking each of them case by case, what we can do is just make a plot. Plots are amazing to visualize our results. So I use this function from matplotlib, which plots these energies, specifically the energies from Q1, as a function of C, and then I attach a label to it so we can distinguish these curves from the other. I do the same for Q2 and the ground state. I put some labels on the axis of my plots, namely the value of C and the value of the energy, and then I put a legend so that I can easily interpret all of them. Let's run. And there you have it. So you see, C goes from 0 all the way down to -3. For C equals 0, you see that the green line, that is the ground state, coincides with the energy from Q1. This is the energy of these states down here. So we'll see that from 0, the ground state is still the same at -0.5, -1, and then somewhere around -1.5, the ground state has an energy that is actually lower than the energy of this state. So this point here, that is somewhat higher than -1.5, is the answer to question number 3. On the other hand, you see that the ground state energy goes down, and at some point it crashes onto this line. And this line is the energy as a function of C of this state over here. So the answer to question 4, at which value of C this becomes the ground state, can be obtained by looking at which point the green curve and the orange curve coincide, which is somewhat below -2.0. So this is the last exercise, and I think this is a very nice example of how useful are plots. You see, just by looking at this figure, you can get much more information that I could tell you in a lot of words. So use plots. Plots are great, and they're great for explaining stuff. And especially if you're going to work in the future on projects with Python, you are going to see and use plots a lot. So this concludes on my end the presentation. If you have anything you want to discuss, please type in the Q&A. So, was it everything clear? It would seem so. Yes, I'm very happy. Any feedback? Anything you want to say? Oh, thank you for attending. Thank you very much. Then yes, you just need to change the values of the parameters, reevaluate the cell, rinse and repeat how many times you want. Thank you very much. for your appreciation and thank you for attending. I'm very happy that you could enjoy and use this. I think that Python is really a useful and fun programming language to use. And at least for me, it was extremely useful in my line of work. And I think that in general, it's very good to be able to play with this stuff and to stimulate your own curiosity. It's just going to be so fun and so useful in life in general. And especially if you're going to do data analysis or AI or whatever path you're going to follow in the future, just being curious and liking to play with this stuff is going to help you a lot, I think. So I think that I can finally conclude. This is the end of the Python for STEM. Thank you so much for attending. And if you have any other question, you can email one of the organizers. And yeah, glad that you enjoyed. Bye-bye, everybody.